Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Take a moment to savor the crust of a perfectly baked loaf of sourdough. That complex aroma, the nutty depth, the rich, mahogany color, it's pure culinary magic. We usually credit the baker's skill, the yeast, and the heat. But what if I told you that the secret ingredient, the silent accelerator of flavor, is quantum mechanics? That's right. The delicate dance of flavor compounds in your kitchen is being controlled by a phenomenon called quantum tunneling. This isn't just about chemistry. It's about subatomic physics altering the kinetics of baking at the most fundamental level. Let's dive into quantum flavor mechanics. When we talk about the flavor and color of baked goods, we are overwhelmingly talking about the Maillard reaction. This is the mother of all browning reactions, where sugars and amino acids break down and recombine under heat, producing thousands of distinct flavor and aroma compounds. Things like pyrazines, responsible for nutty, roasted notes, and melanoidins, the source of the rich brown crust. Traditionally, chemists view reactions like these through a classical lens. For a reaction to occur, molecules need enough energy to overcome an activation energy barrier. Think of it as a small hill. You have to push the reactants hard enough, i.e., heat them up, for them to get over that barrier and react. But that's where the quantum world steps in and throws out the classical rules. In the strange realm of the very small, particles don't always obey common sense. They can exist as probability waves. If this probability wave overlaps the activation energy barrier, the particle doesn't have to climb the hill. It can simply tunnel through it. This is quantum tunneling. It's usually associated with nuclear physics or semiconductors, but it becomes critical in organic chemistry, especially when dealing with the lightest atom, hydrogen. Hydrogen atoms, or more accurately, protons, are involved in key intermediate steps of the Maillard reaction. Flavor creation is heavily reliant on the rapid transfer of these protons between molecules. Because hydrogen is so incredibly light, its wave-like properties are pronounced, making it an excellent candidate for tunneling. When you bake bread, the heat is providing the classical energy needed for the large molecules to jostle and interact. But the tiny, nimble hydrogen atoms aren't waiting for the energy boost. They are tunneling through the reaction barriers, effectively shortcutting the process. This subtle, subatomic acceleration dramatically changes the asterisk rate at which certain flavor compounds are formed. Crucially, quantum tunneling often favors the creation of specific, more complex isomers and byproducts, the very molecules responsible for the savory depth we crave in artisan bread. If the hydrogen atoms had to wait for the full classical activation energy, the reaction cascade would proceed differently, yielding a less sophisticated, blander profile. Now, how does this link directly to the type of bread you eat? Think about the difference between a quickly baked loaf of soft white bread and a slow-fermented, long-baked sourdough. Industrial baking prioritizes speed and volume, often using high heat for short durations. While this triggers the Maillard reaction, the speed minimizes the time available for quantum tunneling to exert its long-term influence on the kinetic pathways. The resulting flavors are simpler, often just toasty or sweet. Artisan baking, however, involves long, slow fermentation and often lower, sustained baking temperatures. This maximizes the window of opportunity for quantum tunneling to accelerate those subtle, proton transfer steps throughout the entire matrix of the dough. Over an hour in the oven, countless billions of hydrogen atoms are tunneling, pushing the complex flavor chemistry towards a richer, nuttier, more intense endpoint. This is a fantastic example of emergent complexity, a physical phenomenon described by Schrödinger's equation, a rule of reality so small it seems utterly disconnected from our everyday experience. is precisely what separates a delicious, complex sourdough from a standard supermarket loaf. The quantum world is literally flavoring your food. So the next time you bite into a piece of perfectly baked bread, remember you are experiencing a direct consequence of probability waves and the fundamental laws of the universe, right there on your plate. For more incredible facts like this, don't forget to subscribe and turn on notifications.